Okay, so in this video, we're going to go over why certain groups that don't need electrons, like OH groups and NH2 groups, direct incoming groups, such as an NO2+, or really any generic incoming group, in the ortho and para position and not the meta position. So this one's the para position. This one is the ortho position. This one is also the ortho, just the symmetrical opposite. This one's the meta, and this one's also the meta. And these incoming groups are not directed to meta whenever you have a donating group. And we're going to go over the reason why. Of course, you can just memorize that, but it's actually much better if you understand why it's directed the way it is. Okay, so let's go ahead and draw the first resonance structure we get if I add in that position right there. So the ortho position. So it's going to look like this. You have our OH group coming off the top still, right? We have these lone pairs. And if we're gonna add this here, we're gonna obviously move these electrons from here into that bond right there, and we're gonna have a plus charge over here. So that's one resonance structure right there. There's another resonance structure we can make if we just move these electrons up into that double bond and give the O the plus charge, right? We can always do that. So let's go ahead and draw that one. And that's gonna be the result of moving these electrons down here, which will give us this. The plus charge is now there, this is here, this hasn't changed, and we have an NO2 here. But we still have some more resonance structures we can draw. Let's draw some more. Well, this is kind of the hardest one to see, but if I move these electrons down to here, right? And I move sorry, not there. If I move these electrons up to that oxygen, and I move these electrons right here, I can add a positive group right here. So let's go ahead and draw that one. That should look like this. This one doesn't change. We now have a plus sign here, and we have a nice OH group over here, a double bond here, and again that NO2 group. And we still have one more resonance structure where we can add our positive charge right here. So let's go ahead and draw with a red marker how that's gonna happen. This is gonna jump right here, and this positive charge is gonna end up right here. So let's go ahead and draw that. That's gonna look like this. Plus charge right here, double bond right here, double bond right here. We still have an OH, and we have our NO2. And if you look carefully at all the hydrogens where they are, you'll see that this does in fact work perfectly fine. Now I'm gonna draw the meta resonance structures, okay? So meta is if I add in this position right here, okay? So let's go ahead and draw that real quick. So our first one is gonna look like this. It's gonna look like, if I get rid of that, it's gonna be if let's do it where I move my electrons into here. Okay, so I'm gonna have a plus charge right here. So let's do that, let's draw that out. I'm gonna have my plus charge right here. I'm gonna have my NO2 added right there. I'll still have this double bond. I'll still have this double bond, and I'll have my alcohol group up there, my hydroxy group up there, okay? Now let's go ahead and move some stuff around. I'm gonna go ahead and move this right here. Oops. I'm gonna move this right here. Let's put it in red. I'm gonna move this bond right there, and our plus charge will end up right there. So that should look like this. We still have my NO2 right here. Still have our OH group right here. This double bond's gonna stay there, and then we're gonna have a plus charge right here. Okay? And we're gonna have our double bond having moved there. I think we only have one more option here, right? The only other possible resonance structure is gonna be if I move these electrons right here, and I put my plus charge wherever I have a lack of electrons. So I have my double bond here, I have my NO2 group right here, and then I have this double bond, I still have my OH, and I have a plus charge right here, okay? And there's actually no other possible way to put a resonance structure here, okay? There's only 3 potential resonance structures. There are more theoretical resonance structures you could draw, but those are all gonna be super unstable, and we wanna go for the most what are all of our possible stable resonance structures with only one plus charge? Because theoretically I could add negative and plus charges everywhere here and get a really messy set of resonance structures going. So let's go ahead and draw our last one. Let's draw our para position. So para is going to be if I add in this position right here. And there's only one of those. So if I were to add right there. Okay. So let's go ahead and do that. I'm going to zoom in here a little bit. So let's draw our first one. We still have our OH right here, and we still have our NO2. And say the way let's say we got this by breaking this bond right there and getting a positive charge right here. That should look like positive charge. We should have this double bond still here and this double bond still here. So what's the other resonance structure that comes off of this? Well, we could move this double bond into here and we'll have a positive charge right there. So let's do that first. We'll have this double bond hasn't changed. This NO2 is still the same. Obviously it's attached the same way. And now we have a plus charge here and we have a new double bond right here. Okay. This is where a lot of students don't see one, and it's honestly the most confusing one, but we have lone pairs right here on this oxygen. We can theoretically bring this down, get rid of our positive charge here, and give our OH a positive charge. Because then it'll have one pair of lone pairs, so that's one, double bond which counts as two, right? And we'll have a hydrogen. And those two electrons, that gives us 5. So it'll have a formal charge of +1. So let's go ahead and draw what that looks like. That looks like this. With our NO2, these double bonds haven't changed. And instead of a single bond here, we're going to have a double bond and an OH, which has our plus charge on it. And now the final resonance structure is actually even harder to see if you don't like arrow pushing. But what we can do is we can pull these electrons that we just moved up to here, right? Getting rid of that positive charge, and then moving these electrons over here. And where does that positive charge leave us? It leaves us with a positive charge right there, which looks like this. We still have this double bond, we still have this NO2, our OH is now neutral, we have our new double bond right here, and we have a positive charge on that carbon right there. So as you can see, and this is our last and final resonance structure, as you can see in the ortho and para position, we have how many resonance structures? 1, 2, 3, 4. So we have 4 total resonance structures for ortho. 4. How many for meta? 1, 2, 3. So we have 3 here. And we have 1, 2, 3, 4. 4 resonance structures here. And this is why when you do experiments with adding substituents to an already substituted benzene ring, you're going to have the vast majority of your products being in the ortho and para position because they're simply much more stable. They have more resonance structures available to them, and you can delocalize those electrons much easier in the ortho and para positions and not so well in the meta position. And this is kind of the long form, explanation as to why OH groups and other electron donating groups like NH2 and OH direct their incoming groups to the ortho and para position. Okay? But you can just memorize that for the exam. But if you want to understand it, this is it.